are going to simulate the 2D simulation of the piezoelectric nanogenerator cantilever beam. We will first click on model wizard, then 2D, then we will go to structural mechanics, select the piezoelectricity. We can either right click on it or we can click here add. We can see that piezoelectric effect is added. Then we will go to AC/DC, select electrical circuit, add, and then study. Then we will select the frequency domain. We have to double click on it. This is how the model wizard window looks. Then we will go to parameters. We will define the parameters that we are going to use in our simulation, such as the name. The expression, the name defines the variable, expression defines the value of it, and this is the description. ACC defines the acceleration that we are going to apply on this cantilever, and R load defines the load resistance. Here we will define the value of it, which is 12 kilo ohm. And W plate defines the thickness of the cantilever beam. Sorry, width of the cantilever beam, which is 14 mm. We can change it according to our need. Then we will go to geometry, select the length unit to mm, as we are going to create this cantilever beam in millimeters. Then we will right click on geometry, select rectangle, then we will specify the positions of it, -1 and -1. Then please click on build selected. As you can see here that in the graphics window, the block is created, rectangle is created. Then right click on geometry, then again select rectangle. Then we have to specify its width and height in size and shape menu, and we have to specify the x and y coordinates of it. Rectangle 2 defines the cantilever beam. In the layers menu, we have to differentiate the W plate layer in different, split in different layers. W plate in different layers. Then build selected. By clicking on this button, we can see here the whole cantilever, whole geometry. This is the cantilever beam, and this is the first rectangle. Then we will right click on geometry again, then select rectangle again. We will define the width and height, the size and shape menu. will specify the x and y coordinates. Rectangle 3 defines the proof mass. We selected, we can see here the proof mass is created. Then right click on geometry again, go to booleans and partitions and select union. Click on this graphics window, use the shortcut Ctrl A. By selecting this option, the layers R1, R2 and R3, means rectangle 1, rectangle 2 and rectangle 3 are selected. Then we have to uncheck this block, keep interior boundaries, then build selected. Then we will go to geometry, right click on it, go to chamfer, we will select these 2 points where we want to create the chamfer. In the distance menu, from distance from vertex, we have to insert the value 0.25 mm. Then go to build selected. In this menu, now we will click on rectangle 2 and duplicate it. It is named as rectangle 4. And then we will go to geometry again, right click on it and select line segment. I forgot to mention that we have to also build rectangle 4 by selecting build selected option. By selecting line segment, now we have to specify in the starting point, we have to convert from vertex to coordinates, and same as in the endpoint menu. Then we will specify the starting point xy coordinates and the endpoint xy coordinates. Then we will build selected. Then right click on geometry again, select line segment again. We have to do same as from vertex to coordinates in both starting point and ending point. We have to specify this line segment. Then click on build selected. By clicking on this button, we can zoom a specific section. This is line segment 2 and this is for line segment 1. And by clicking here, we can see the whole geometry again. Then we will go to form union and build on. The form union makes a union of this whole geometry. Then we will go to materials, click on material. Sorry, I opened it initially. I'll close it first. Then we will go to add material. Then we will go to piezoelectric section. Select piezo lead zirconate titanate piezoelectric PZT5A. We have to double click on it or either right click and add. Then we will go to built-in section, select structural steel here. Then we will click on structural steel here. Select manual here and paste the selection. We have to define what layers will act as structural steel layer or substrate layer. Here we have defined the layers which will be structural steel. Then we will go to solid, click on solid mechanics linear elastic, go to attributes and click on damping. Then in the damping settings, we have to select the damping type as isotropic loss factor and I select here user defined. Then we have to define the value 0.001. Then we will go to piezoelectric material. all domains to manual, delete the selections, and the paste selection again. We have to enter the manual values. Here we define the layers, which are layers of the sections which will act as piezoelectric material, piezoelectric layer. Here the layers are shown. Then in the same piezoelectric section, we will click on attributes and click on mechanical damping. Here again in the damping settings, we have to select the damping type as isotropic loss factor, and again in the user defined we have to enter the value 0.001. Then we will go to domains, click on body load. Here we have to select all domains, as the body load is going to be applied on these all the nodes, all the domains. Then in the force, we have to define in the y direction this equation. This equation defines the body load that is going to be applied on this cantilever beam. It approximately equals to 9.8 Newton meters per Newton meters per. Then we will go to boundaries, select fixed constraint. We will be selecting this point, as this layer is going, this part is, or this section will be going to be fixed in the whole simulation. And we will go to electrostatics, delete all the selections and paste these selections. Two, 4, 5, 7, 8, 10. Okay. The layers are selected here. Then we will define the thickness to W plate that we had defined earlier in the parameters section in the starting. And we will go to boundaries, select ground. And then in the paste selection menu, we have to paste the values. These values define the layers which will act as a ground: 4, 9, 13, 18, 20, 26. Okay. We can see here the layers which will be acting as ground. Then again we will go to boundaries and select terminal. And again paste selection. Six, 8, 15, 17, 22, 24. These values define the layers which will act as terminal. Then we will go to electrical circuit. Click on resistor. Sorry, I forgot. We have to click on the terminal again and select terminal type as circuit. Then we will click on the resistor that we have added first. In the level N, we have to give the name to N0. And the resistance value that we have defined already in the first section in the parameters menu, R load, R underscore load. Then we will right click on electrical circuit, select external couplings and external 1, terminal 1. Then give node name as 1 and select terminal voltage ES term 1 in the external terminal menu. Then we will click on mesh in the above menu. Click on free rectangular. Then we will select size. Click on custom. We will be giving the maximum and the minimum element size of the triangle in MEMS, which is 0.02 mm. And this minimum size element size is 0.002 mm. Then we will click on study. Click on frequency domain. We have to add the frequency here. We will give the start and stop. Start is 62 from 62 Hz. In the step size is 1, and we will stop at 80 Hz. Click on add. And then we will go to study, show default solver. There is one function in COMSOL Multiphysics that it checks for errors automatically. So we have to deactivate it. So in the solution 1, so as we can see that so go in the component menu, right click on it, sorry, in the definitions menu, right click on it. Then we will go to non-local couplings and select integration. I forgot to do that. We will select selection as all domains. So this setting integrates all the geometry. Then again we will go to solver configurations, select direct in the stationary solver, go in the error menu, check error estimate, switch it from automatic to no. As I said that COMSOL has the function that it checks for errors automatically, we have to select it as no. Then we will click on compute here. This will take some time. I'll skip forward. So this graph appears after the finishing of this computation. This defines the von Mises stress, the stress that is going to be applied on this cantilever beam. Then we will go to again study, rename it, as we are going to add more than two or three studies, so the names should not be similar to each other. That's why we are renaming it. We will rename the first study as frequency response. Then we will click on results. Here we can see that add plot group, 1D plot group. Here we will rename it as frequency response. Voltage and power. So this first graph will define the relationship between voltage, power and frequency. Then we will go to title. From automatic we have to create select manual, and then give this title again here, frequency response, voltage and power. This gives the name to the graph. We have to right click on it, frequency response and voltage power, and select global. Then in the global menu we have to do the expression. This is same as the parameters menu. You have to write as it is. So the unit here appeared is W, that is watt. We have to convert it in milliwatt. We have to see the values of output values in the milliwatt. That's why we'll write M here and give the description. Mechanical power in milliwatts. Then again we have to convert it in milliwatts. Write a small m before it. Then we will go to coloring. We will go to coloring and style. Specify the width as 2, and from marker we have to select cycle. And from positioning interpolated to in data points. Then we will plot from this button. We can see here the graph from with voltage and power with respect to frequency. Then we will go to home again, add study, frequency domain again, here, close it. So this here is study 1 and this is the study 2. Click on the frequency domain. We have to go to frequency as 70.5. in the study extension we have to click on auxiliary sweep and click on add and select the R load here and give the parameter value list as 10 cap. 10 cap range bracket 2 comma 0.25 comma 5 bracket complete. Then we will give a label to it. As I said earlier that the label should be different from the previous studies. We will name it as this load dependence rotation power. Uncheck this box, generate default plots. Then click on show default solver. You have to do this process again of the error checking and deactivation. Click on stationary solver, click on direct. In the error menu we have to select no. Then we have to compute from the above button. This will take some time again. I'll skip forward. Then again we will go to results, right click on the frequency response and duplicate it. As we have to see the other graph, we don't have to do the initial settings, that's why we are duplicating it. Then again rename this graph load dependence rotation power. Copy the whole level, select from data set, we have to select load dependence, copy this level and paste it in this title. We are going to give the title to the graph. Then we will go to legends and select the position right to upper right to upper left. So the graph here will show up, or if it doesn't we have to click in this on this button and plot again. Then we will go to home again, click on add study, again frequency domain, click on the frequency domain here. We will enter the frequency as 70.5 Hz. Again check the auxiliary sweep, click on the add button and select parameter name as ECC. We will give the parameter value list. We have to write the same. Zero point 0.025 comma 0.025 comma 2. Then we will click on frequency domain again. We will change the label of it, give it as acceleration dependence. We'll copy it, uncheck this box, generate default plots. Then again in the study menu we will go to show default solver. Click click on the solution 3, stationary solver 1, click on direct, change from automatic to no, and then compute in the above menu. It will again take some time. Then we will go to, so this won't take much time. Then we will go to this graph, load dependence and voltage. Again right click on it and duplicate. We will rename it as acceleration dependence. Again we will select the give the title same as the above. We will select the data set, as here are three studies. First is frequency response, load dependence, and other is acceleration dependence. Here we can see that these studies we have to see the graph of this study. That's why we are going to select this data set, acceleration dependence. We will go to plot settings, check the x-axis label block, rename it as this. Then we will uncheck this axis is log scale. The graph should appear here, or we can click on this plot button. Here we can see the three graphs.